An equation of the form a cos x plus b sin x equals c can be written in the form a cos of x plus d equals c, where a, b, c, a and d are constants. So you see, we can take this sum of trigonometric functions and write it as a single trigonometric function. So we will end up reducing this trigonometric equation to a simple trigonometric equation. Before I do an example, I will prove this. So to prove this, we look at cos of x plus d and we apply a compound angle identity. So this is the identity that we will apply. We will apply this to cos of x plus d. So we just replace a with x and b with d. Now we want to multiply this by capital A, so we have a number in front of cos, so I can just stick a capital A in here. So now we want to compare all of this here to this here, show that we can equate them, and in the process we can find relationships between the constants a, b, c, a and d. So we want to write this sum of trigonometric functions as a single trigonometric function. So let's compare these. Of course we have the cos x here and sin x here. So you can see that we want a cos d to equal small a. So I'll write that down. And we want minus a sin d to equal small b. That's a plus b here. Now we can take this equation and divide it by this equation. So I'll divide the left hand side of this equation by a cos d, and I'll divide the right hand side of it by a. So we're dividing both sides of this by the same thing, because a cos d is equal to a. But you see, when we do the division here, the a's cancel out. We have sin d over cos d, that's the definition of tan d. And we have b over a. So now we have a connection between d, b and a. Now we will be interested in getting capital A in terms of small a and b. So we'll use this equation here, tan of d equals b over a. From this equation we can get the cos of d and the sine of d. And then we can write a in big A in terms of small a and small b. So we just construct a right angle triangle here. This is minus b over a. Now sin d and cos d can be worked out by constructing this right angle triangle. So Pythagoras will connect angle d with the sides of this triangle. And it doesn't matter actually what a and b are. You know, d doesn't even have to be an acute angle. This will actually work for any angle d. Anyway, we can just pretend that we can construct a right angle triangle and everything will actually work out, even if, you know, say one of these happens to be negative. A could be negative, but we'd be squaring these quantities anyway. We can just think of magnitudes, and the longest side is going to be root a squared plus b squared, and from this we can write down sine and cos of d. Well, if you're still unsure why an acute angle you know, leads us to the correct expressions for sine d and cos d, we see here that cos squared d plus sine squared d will equal 1, and that's an important relationship. No matter what angle d is, whether it's an acute angle or whatever, we know that the coordinates of a point on a unit circle are defined to be cos d sine d regardless of what d is. So for example, d could be an angle between 90 and 180, so we can't even draw this picture. But cos squared d plus sine squared d equals 1. That's still the case because of the properties of the coordinates of this point. The distance of this point to the center of the circle is 1. So basically this has to hold, and it does hold. If you square this and add this onto it, you know, if you square this here, well, let's square this one. You'll get a squared over a squared plus b squared. If we square this one, we get b squared over a squared plus b squared. And if we add these together, we get a squared plus b squared over a squared plus b squared. That's equal to 1. So that property holds. Also, if we take sine d and divide by cos d, we get tan d. If we take this here and divide by this here, the roots will disappear, and we'll end up with minus b over a. So even though I used an acute angle to get out sine of d and cos of d, d doesn't have to be acute. It will work from the properties of the unit circle. Now from back here we see that a cos d equals little a. So I'll write that down here. A cos d equals little a. But if we rearrange this equation here, we see that root a squared plus b squared times the cos of d equals little a. So these have to be the same. So the a here, the amplitude if you want to call it, must be equal to root a squared plus b squared. So that's the first relation that we've shown. And the other one is what we had earlier, tan of d equals minus b over a. So if we get an equation of this form here, we now know that we can write it in this form. Now this might look like a mess, but the root a squared plus b squared is the capital A that we have here, and d, this constant here, is inverse tan of minus b over a. Now of course you could just memorize this formula. Well, nobody in the right mind would probably memorize this and apply it. Let's just apply this. Let's solve the equation root 3 cos x minus sine x equals 1 for x between 0 and 2 pi radians. So we see that this expression here has the same form as this expression here. So by comparing, we can note down what small a and small b are. And then we can just plug them into this to get this simpler equation. And well, you know, we can also get d by getting the inverse tan of b over a. Actually a is root 3 in this case. B is minus 1. Okay, if we compare this to a cos x plus b sine x, then we just plug in for a and b here, we get this simple trigonometric equation. C is the number on the right hand side. C is 1 in this case, so we put a 1 here. And then it's quite straightforward to solve. Now, suppose you haven't this thing memorized. Well, let's just let's go through it without just plugging numbers into this formula. Well, what you do, of course, is you compare it to a cos x plus d. So that's what we want to write this. That's the form we want to write this thing in. And you just look up the compound identity for this thing, and you know, you just multiply by this capital A. So you get a cos x cos d. We already had this earlier. Minus a sine x sine d. And you just compare this to this thing here, and you can see that a cos d must equal root 3 in this case, and minus a sine d must equal minus 1. I'll do that in a different color. Now, as we've seen already, if we divide these, we get tan d. So just quickly run through this again. It's just repeating the proof for a specific example, really. We have minus sine d over cos d equals minus 1 over root 3. Well, sine d over cos d is, of course, tan d, as we've seen, equals minus 1 over root 3. So then the tan of d is 1 over root 3. Construct a right angle triangle. Work with an acute angle d. As I said already, it doesn't matter what d is, but this triangle will give us the correct expression for a. Tan of d is opposite over adjacent. So the hypotenuse then is got from Pythagoras, so root 3 plus 1, or root 4. So the cos of d is adjacent over hypotenuse, root 3 over 2. Of course, the hypotenuse must be a. because cos of d is root 3 over a. So that's a worked out, and we also have d. Well, we know that d is the inverse tan of 1 over root 3. Now, the inverse tan of 1 over root 3 is 30 degrees. So indeed, d happened to be an acute angle in this case. It doesn't have to be, of course. Anyway, we can now write our equation as capital A cos x plus d. So capital A was, remember, the square root of this squared plus this squared. That's the square root of 4, which is 2. And d is the inverse tan of minus b over a. So it's the inverse tan of minus 1 over root 3, or the inverse tan of plus 1 over root 3. Okay, so now we have a simple trigonometric equation. We just have a single trigonometric function. So to find x, we get the inverse cos of a half. Now your calculator will give you an answer of 60 degrees. So we need to get the other answer. So we want to see in which quadrant is the cos function positive, and we know it's the C quadrant and the A quadrant. So you know, the x value of this point here is a half. I won't bother writing in the y value. We just want the cos. And in the C quadrant as well, the x value has to be a half. It'll be plus a half. So we look into C and A. Well, the A quadrant is a given from the calculator. So we need an angle in the C quadrant. That is an angle between 270 and 360 degrees. So we're measuring anti-clockwise from the positive x-axis to here. How do we find that angle? Well, the reference angle in here is 60 degrees. Just reflect this through. So the angle that we're interested in is 360 minus 60, which is 300 degrees. You can go to your calculator and check that the cos of 300 is a half. Okay, so we can also add multiples of 360 onto these angles. So n is some integer, it's a whole number. And we still have solutions. As I've said before, we can add 360 onto an angle and we're back to where we started. So the sine or the cos, the coordinates of the point are not affected. So we need to just check that we get all the solutions x in the domain we're interested in, which is from 0 to 360 degrees, or 2 pi in this case. Okay, so that's x plus 30. So we found the angle, but we want x, so we just subtract 30 degrees. So we get 30 plus 360n, or 300 minus 30 is 270 plus multiples of 360. So now we know what the solutions are. We don't have to add 360 onto 30. If we do, we get 390, and 390 is outside this range here. Similarly here, we don't have to add on multiples of 360 to 270, because if we do, we'll get angles that are outside this range. So there are just two answers: x equals 30 degrees or x equals 270 degrees. In radians, 30 degrees is pi divided by 6, 180 divided by 6, and 270, well, that's 9 times 30, that's 9 pi over 6, that's 3 pi over 2 radians.